Hello everyone, I'm Hiroto Tamura from Tokyo Metropolitan University. We participated in multimodal task English-Japanese and will introduce our submitted system. In multimodal machine translation, available data is relatively low resource compared to other text-only data because MMT requires text paired with images. To overcome this issue, we augment training text and images using several methods without external data. Additionally, we introduced the Dropnet Method to effectively utilize the features of both text and images. This is expected to regularize the network when training. Next, we introduce or use the models in this work. RNN-MT is an attentive encoder-decoder model. The encoder is bidirectional GRU and the decoder is conditional GRU. Our MMT model with decoder initialization is based on our NMT model's architecture, and this MMT model initializes the hidden state in a decoder with visual features. This architecture is used for MMT models using augmented data. Our MMT model with double attention mechanism, the decoder part of this is an extension of our NMT model to multimodal. While decoding, this model individually pays attention to the source sentence and image, and obtain a textual and visual context vectors. Combining obtain each context vector in another attention layer, we obtain multimodal context vector and use it when decoding. Then, we introduce the Dropnet method. This is proposed to fully utilize two different types of features in a translation task. This aims to regularize the network training by probabilistically dropping either the feature when combining features. We incorporate this method into MMT with the double attention model. This probabilistically drops either the textual or the visual context vector when combining them to obtain a multimodal context vector in a decoder. More specifically, at each decoding step while training, with probability p-net half, either the textual or the visual context vector is selected to compute the multimodal context vector. With probability 1 minus p-net, both context vectors are used for multimodal context vector. Next, we introduce our data augmentation method and how to use augmented data. For textual data augmentation, sampling, this method samples hypotheses from output distribution at each decoding step. Random noising, this penalizes every hypothesis on the beam by adding noise R beta to its hypothesis score. R is a sample from the uniform distribution on the interval 0 to 1, and beta controls the noise intensity. Here are some examples of noisy sentences generated with the random noising method. To augment training text, we train a text-only transformer model on the original training text. And then we translate the original training text into synthetic training text with the trained model. Furthermore, we combine different types of noisy text for pre-training. For visual data augmentation, center cropping, this crops the center part of each image. Random cropping, which randomly selects a part of each image and crops it. Rotation, which rotates each image right or left on axis between -20 and 20 degrees randomly. We explain training procedure for the models using augmented data. We pre-train only our MMT with the decoder initialization model on the augmented data, and fine-tune on the clean, that is original training data. For details about the training with the augmented text, we place noise on the target side in addition to the source side. So text used for pre-training consists of augmented text on the source side and clean text on the target side, or augmented text on the target side and clean text on the source side. For using augmented images, we pre-train the model with the clean text on both sides and augmented images. Next, we describe the experimental setup. For training and validation data, we use the Flickr 30K entities dataset for English, and the Flickr 30K entities Japanese dataset for Japanese sentences. And the images are in the Flickr 30K dataset. For testing, both language tickets are given by the organizer, and the images are in the Flickr 30K dataset. About preprocessing, We lowercase, normalize, and tokenize English sentences with the models, and also tokenize Japanese sentences with the makeup. For vocabulary, we use word-level vocabularies of 9,546 items for English and 11,235 items for Japanese. We use these hyperparameters for our NMT, MMT with decoder initialization, and MMT with double attention models. Dropout words are applied to source embeddings, source annotations, and pre-softmax activations, and is shown in the table below. Next, we show our results and conduct analysis. At first, we describe the model's notation. Here are a few examples. First one, the model acts as pre-trained on the augmented text generated by randomizing method with beta 5, and the augmented text are on the source side. Second one, the model acts as pre-trained on the augmented text mixed up with two types of noisy text. Here, those are generated by sampling and randomizing with beta 4, and the augmented text are on the target side. Here are the published results for English to Japanese. 4 models from top are single models, and the others are ensemble models. Ensemble top 6 models is the best in the below metric, but for IBs, ensemble of 3 models with Dropnet method is the best. For Japanese to English, although ensemble top 6 models is the best on the dataset, ensemble 3 MMT with decoder initialization models achieves the highest blue score on the test set, and ensemble 3 MMT with Dropnet is the best for IB's score. We examine the effectiveness of the Dropnet method. From this table, models with Dropnet are better than without ones for each direction. This shows incorporating the Dropnet method into MMT with the double attention model can help improve the translation performance. This is our translation result on a dataset for bus directions when using augmented data. Each model is trained 3 times with different Cs, and it scores average of 3 model scores. For English to Japanese, looking at the left table, we chose these beta values because model of randomizing method with beta 5 has achieved the highest score among the ones with other data augmentation methods, followed by beta 1 and beta 6. Also, these beta values are used for mixed model. The models with randomizing method are relatively better than the ones with other data augmentation methods. The models using visual data augmentation are better than the ones not using augmented data, but the differences are marginal, so we did not conduct experiments with augmented visual data for Japanese to English direction. For Japanese to English, in contrast to English to Japanese results, NMT is the best than any other models. We investigated how the score is affected by whether the noise data for pre-training is on the source side or the target side. From this table, placing noise on the target side is better than on the source side for both directions. Although it is unclear why the noisy data on the target side is effective, we infer this setting is useful under low resource or MMT situations. Next, we show some translation examples focusing on the ensemble top 6 models' good translation. Only ensemble top 6 models describes that a man is painting a face on the ground while kneeling. On the other hand, other models describe a man is painting a face on his knees. We show some translation examples focusing on the ensemble top 6 models' poor translation. NMT and MMT with decoder initialization models describe an older man wears an orange cloth, but the other models describe an older man wears an orange laptop. For conclusion, we found the Dropnet method is effective compared to not using Dropnet. Data augmentation is useful for the English to Japanese direction. The randomizing method possibly affects translation performance compared to other data augmentation methods, and placing the noise on the target side is more effective than on the source side. For future work, we'll investigate why placing the noise on the target side is effective, and study how the Dropnet method works in MMT with double attention models. Thanks for listening.